Hey there, today we're going to be looking more at two variable equations, their graphs, and at the points and determining whether or not they fit the line that the graph would make. So looking at this first one, we know in an ordered pair the first coordinate is x and the second coordinate is y. And we are given a two variable equation, 3x minus 7 equals y. In order to determine if each of these points belong to the line, if they're solutions, we simply substitute them back in to the equation and see if it works. So we have 3x minus 7 equals y, and instead of x I'm going to go with 9, and instead of y I'm going to go with 20. So that's 27 minus 7, and yes, that equals 20. That tells me that point A is a solution to this equation. So if I were to solve an equation, if I were to solve a problem that had this equation, x equals 9 while y equals 20 would work. So I can go ahead and plot that point, 9, 20. There's my point A. Even if it doesn't work, I'm not going to plot it. I'm going to repeat the same thing with B and C. So for B, 3 times 5 minus 7, I want that to equal 0. And nope, 15 minus 7 does not equal 0. So B is a no-go. C, I need to do 3 times 3 minus 7 equals 2. And 9 minus 7 is 2, so that one's good. So I can plot 3, 2, that's point C. And then in order to connect the points, because that's the last part of the equation, I need to make a straight line that goes through both of them. So I'm going to kind of estimate it first and then let it straighten out. So if I were to graph the equation y equals 3x minus 7, that's the equation in this problem, all of the solutions would lie on this line. And I know I estimated my line's not perfect, but if we pretend my line is perfect for a second, I know that, this might be 611, something like that. That would also work, something around there, not exactly. But that's what a line means. A line means a set of all the points that work when you substitute them into the equation. Go ahead and try the same thing with problems 2, 3, and 4. Pause them, come back when you're ready to move on. All right, hopefully you have paused and you have come back and you're ready to move on to the next set of problems. We're going to look more at the relationship between x and y here. The problem at the top says, suppose a motion detector tracks the time and distance traveled as you walk 40 feet in 8 seconds. The results are shown in the graph below. Use them to answer the questions. The challenge here is to match up the descriptions at the bottom with the graph that could have been plotted that represents that. So take a second, pause the video, see if you could match up A, B, C, D, and E with graphs 1, 2, 3, 4, and 5. You're going to put the numbers of the graph that you think it matches up with right down there. And you could use process of elimination. There's not any extras, not any repeats. Unpause the video when you're ready to come back. All right, so hopefully you've gotten started. To me, the one that I think is kind of the easiest to start with is A. First of all, it's the shortest and simplest. And second of all, I think it's just going to be the easiest to interpret. Here I see a keyword of steady. You walk at a steady pace of 5 feet per second. To me, that tells me that that's going to go with graph 3. There's no other graph that is as simple enough to convey the idea of steady. All the other ones are doing wacky things. So to me, that creates a rule that when I see the word steady, I need a straight line. If you need to pause the video at any point while I'm teaching this and go back and fix your answers and try to rearrange some of your answers, you can, because that might have given you a clue. So then the next thing I want to do, I want to scan the other options, and I see that D also has steady and steady again in there. So that means I can look for other things that have straight lines, and to me that's graph 5. I can see that this must be the steady portion this must be the pause, and then this must be the next steady portion. So that creates another rule. Pause is going to be like a horizontal line. So steady, the straight line looks more like that. Pause is a horizontal line where you're kind of not making any progress. So I'm going to look and see if there's anything else that has pause in it. I see C has pause in the middle. Rapidly at first, then pause, then an increasing rate. Well, the only graph left that has that kind of horizontal line in the middle would be graph 1. I can see that this could be the pause right here. And then this could be rapid. And then this could be the increasing rate because it's kind of going up wildly. So I think graph 1 is going to fit with that. And then I have 2 left. So I've done 1, I've done 5, I've done 3. I have graph 2 and 4, and I have descriptions B and E. One of them says you walk slowly at first and then increase. One of them says you walk rapidly at first and then slow down. Well, I can look at graph 1 and I see increasing kind of looks like this. And that looks like what graph 4 is saying. And that was in description B, increase at the end. So I think those match. So I'm going to go with graph 4 for that. And then graph 2, this kind of looks like you're slowing down at the end. You're kind of tapering off to almost a pause. So then that goes with E, because in graph E, you slow down at the end. So I think that these are the graphs that match up with each of the descriptions. All right, next page. You're going to do kind of something similar. You're going to read through each of these descriptions and answer the questions based on the graphs. Pause it, try the whole page, come back when you're ready to talk about it. All right, hopefully you've paused and you are back and ready to hear all about these graphs. It's the same type of idea. So let's see where I want to start with this one. So I have something where it's slowly at first and gradually increased. I actually kind of remember what that graph looks like from the last one. I remember increasing at the end kind of looks like that at the end. We have rode quickly and reached early, which tells me that there might be a pause at the end of that one. Started late tells me that there's going to be a pause at the beginning of that one. And then slowed down, I kind of remember what that graph looked like. It was like that where you kind of reach a pause at the end. So let's take a look. So the one that matches Celia's looks like it's going to be graph 2. I'm just going to put the answers over here because that's the increasing at the end. Now they reached the campsite early, so I need a pause at the end. That looks like 4. Started late as a pause at the beginning. That looks like it could be this one, 3. And slowed down, that matches 1. So it looks like we did that right. On the second one, so we have the number of the cars in a school parking lot changes as time passes during the day. And we want to talk about the story that each graph tells. Which graph shows the pattern you expect? So looking at the story here for graph 1, I can say that maybe this little increase right here could be where the teachers are arriving. And then there's a pause, sorry, P, because no cars are coming in the middle of the day. And then there seems to be this like big peak where there's increasing number of cars. So that could maybe be like the visitors. Then the visitors leave. So here's the visitors coming and here's the visitors leaving. There's another pause, and then this could be the teachers leaving at the end. Guess that could make sense. I'm not sure if that big peak really makes sense for the middle of the day, but let's look at the next one. Graph 2. So here, I think this is like all the teachers coming to school. Here, there's this big pause where during the day, the parking lot doesn't change at all. There's the same number of cars. And then this could be the teachers leaving again. That makes a little bit more sense to me. I don't think that big spike in the middle makes sense. So I say that graph 2 shows what I would expect. And then how could you label the graph so someone else would know what it represents? I would think you would put time on the bottom on the x-axis and cars on the y-axis. All right. So here, the relationship between price charged for each sweatshirt and the profit. So the first one is saying that as the price increases, the profit goes up. Like it's a steady relationship. That kind of makes sense. This one is saying that as the price increases, the profit goes up, but then it kind of pauses. The price continues to increase, but the profit doesn't go up. This one is saying as the price goes up, the profit increases, but then after you hit a certain point, the price continues going up and the profit decreases. And then the last one's just kind of a mini version of the same thing. So I think you could kind of make an argument for more than one of these best describing the relationship. Because you could say that this one works because, yeah, as you increase the price, you're earning more money. Or you could maybe say that this one works because as you increase the price, you're earning more money, but if you start making it too expensive, no one's going to buy it. I think you can make an argument for either one. And then for what variables might affect the club's profits, you could say anything like, maybe it's an ugly, shirt. Maybe it's an ugly shirt. If it's ugly, no one's going to want to buy it. Maybe it's bad weather and people couldn't show up to the event where they were selling it. Maybe the person who was selling the sweatshirts wasn't friendly. It could be anything like that. Maybe people thought it was too expensive. These are all things that could affect it. So you could really come up with many, many different things for that. All right. And page 92 is the same idea here. We have lots of different stories, A through G, and we have to match them with the graphs below. Now here, the graphs can be used more than once. And I think you could make an argument for many different graphs fitting a particular story. You just have to be able to make an argument. They also want us to say which variable is the dependent variable and which variable is the independent variable. So let's take a look at an example of that. On A, the number of students who go on the school trip is related to the price of the trip. Now they kind of make it easy for us by putting the variables in italics. So that's a good resource to use. Number of students who go on a trip is related to the price of the trip. Well, I think you can kind of make an argument either way here, but I'm actually going to go with the independent variable being the price and the number of students being the dependent variable. I'm going to argue that if it's too expensive, students won't go, and that's what determines how many students go. But you could make an argument the other way. You could say, as the more students go, maybe the price is able to be adjusted and goes down. So you could kind of make an argument either way with that, but I'm going to go with this being my explanation. And then I have to pick a graph that goes with it. So I'm saying as the price goes up, fewer students are going to go. I think that kind of goes with graph 2. So if I have the price here, because independent variable goes on X, and I have students here, because dependent variable goes on Y, as the price increases, so this could be like $5, this could be like $10, this could be $15, and so on, fewer students go. So when it's cheap, when it's, $5, maybe there's 100 students going. Maybe if it's $10, only 50 students are going to go. When it's $15, maybe only 25 students are going to go. I'm just making up random numbers, but that's an idea of how this works. So I'm going to say graph 2. Pause the video, see if you could figure out the rest, and don't forget that there could be multiple answers. For these, you just have to be able to argue your point. All right, hopefully you've paused the video and you're ready to come back and talk about it. I'm going to erase this off graph 2 in case I need it again for another problem. For B, I'm going to go with the independent variable being time and the dependent variable being the speed. So I'm looking at a half pipe ramp, and it says first we're going down one side, so that's going to be fast. And then up the other side, that's going to be slow. So I want to go, I think I'm going to go with graph 5 for this. So I could say that this is going down the ramp. And then this could be going back up the ramp. You have to kind of, you have to increase your pace over the time. I think I'm going to go with that. Graph 5. C, so we have water level and time. I'm going to go with time being independent variable and water level being dependent variable. So let's see, a bathtub. I kind of like graph 1 for this. So I could say that this is somebody filling the tub, then they stop it. They stop the water. Then it increases again when the person gets into the tub. And then there's another pause while the person takes a bath. This could be person getting out of the tub. And then this could be draining. So I like graph 1 for that. All right, D. So we have waiting time and the people in the park. So I know that waiting time is going to depend on the people in the park. Because the more people that are in the park, the longer the wait time at all of the different rides is going to be. So I kind of like graph 4 for this, because if this is the people in the park, as there's more people, there's going to be more wait time. I think that makes sense. All right, E. The number of hours of daylight changes over time as the seasons change. So the independent variable is going to be time, and the dependent variable is going to be the daylight. The daylight depends on how much time has passed. Let's see which graph. I think you could kind of make an argument for more than one here. Like if you look at graph 3, for example, there's more daylight in the summer and less daylight in the winter. So you could say it goes summer, winter, summer again. Or you could say that something like graph 5 or 6 is just a zoomed in version of that. Like maybe this is summer and this is winter and winter. Maybe this is summer and this is winter. So I think any of those kind of work. But I kind of like graph 3 showing the multiple seasons. If you look at graph 3, then I would say that this would be fall and the upward would be spring. So I'm going to go with graph 3, but you could make arguments for other graphs on that one. All right, so weekly attendance at a popular movie theater changes as time passes from the date the movie first appears. So time is going to be the independent variable, attendance is going to be dependent. At first, a lot of people are going to go to the movie, but then it's going to decrease as the movie gets less popular over time. So I kind of like graph 2 for that. So at the beginning, a lot of people are going to the movie, and then it goes less and less and less people till it's about to exit the theater. So like graph 2. The steady ones, to me, are the easiest to figure out. The number of customers in an amusement park with water slides is related to the high temperature of the day. So the temperature must be independent because the customers are going to depend on what the temperature is. If it's hotter, more people are going to go. So I like graph 4 for that. As the temperature increases, the people will increase. The hotter the temperature, the more people that will go. You could also kind of make an argument for graph 6. Like maybe this is ideal water park temperature. Maybe this is like, 90 degrees. This could be something like, 30 degrees, no one's going to go. And, if it's like 150 degrees, if the sun is exploding, no one's going to go. So you can make an argument for that too. I'm going to go with graph 4 for that. Thank you guys for watching.